The sodium channel is a protein channel. It's made up of a sequence of over 2,000 amino acids. So here the sequence of amino acids is represented by the orange line. And in green here is the plasma membrane, with the outer side and the inner side. You can see here that you have 4 identical domains, called 1 to 4 in Roman numerals, and in each domain you have 6 transmembrane segments, 1 to 6, and a P-loop, which is a sequence of amino acids that is inside the pore. And you have here the segment 4, which contains a regular sequence of positively charged amino acids. You have here so 4 such segments, and this makes the protein sensitive to potential, because when you change the potential, because of the charged amino acid here, the protein changes configuration. This protein folds, and here, when it's in the membrane, the 4 domains delineate an aqueous pore where the sodium ions are going to pass, to go through the membrane. So when here is the sodium channel represented a little bit cut in the plasma membrane, inside the plasma membrane, and when it's closed, no ions go through, and in response to a change of potential to a certain threshold, then the ions, the sodium ions, go through, and you have here a gain of plus charges in the inner side of the membrane. Let's record the unitary current through a single sodium channel. To do so, we record in cell-attached configuration to get a very small piece of membrane underneath the pipette, and in this small piece of membrane, we hope to get 1 sodium channel. Here, it's a muscle fiber and not a neuron. Why do we record the activity of a muscle fiber? It's because there are a lot of sodium channels, and also it's how the researchers did in the 80s to record the first single channel current. They record in voltage clamp mode to get a current, and you have here the recording on the right. So the membrane is held at a potential of minus 90 millivolt. It's voltage clamp mode. And then a depolarizing step to minus 40 millivolt is applied to the patch of membrane. And in this patch of membrane, you can see here that you have no activity, and then an inward current, and then no activity up to the end. The second trial, you have no single channel current. The third also, you have no current. In the fourth recording, here you get an inward current, the same, and then no current. And you can follow like that with different trials, and here you have a very brief opening, underneath no opening, and here a very brief opening, and here an opening, and here no current, no opening. What is this rectangular signal? This is the unitary sodium current, which is written with a lowercase I, and this current has an amplitude and a duration. Here, the currents are redrawn to suppress the noise, and you have here the openings, 1, 2, 3, 4, 5 currents, single channel currents. What do we see? We see that the delay of opening is variable. Sometimes it's long, sometimes it's really short. The duration of the opening is also variable. It varies here, short, longer, much longer here, much longer here. Okay. But the amplitude of the opening is very stable. It means that the intensity here is the same. When you have a current, it means that the channel, which was in the closed state, now opens. So first here, if we look at this here recording here, you see that the channel was first in the closed state. Then it opens. It opens when the membrane is depolarized and a current appears. This current has a certain duration, and then it stops the current. Why is it rectangular? It's because either the channel is open or it's closed. So either there is a current or not. So the channel opens in response to a depolarization of the membrane, and then it goes to a state here that we call here inactivated. Why? Why do we say inactivated and we don't say closed? Because here you see here in the recordings that the channel never reopens. It opens once and it never reopens. So here, for example, it opens once, here once, here once, here once. It means that it goes into a state where it cannot reopen. This state is called inactivated. And then the channel will close again only when the membrane repolarizes. So we have three states of the channel: closed, open, inactivated. Why and when does it inactivate? It inactivates because the channel has been open for a certain amount of time, around 1 millisecond. After 1 millisecond in the open state, the channel inactivates. Why is it inactivates? We will see that later. It's because of the properties of the protein. So it's a voltage-gated protein. It opens with a change of voltage, with a depolarization. And it's also a protein that inactivates. Let's see the conclusion here. The single channel current has a stable amplitude. The latency and the duration of the opening is variable. And there is a maximum of one opening per voltage step. Here, the voltage step that you see here, there is only one opening. Though the membrane is still depolarized, you have no opening here. And you have three states of the channel: closed, open, inactivated. In which direction does the sodium current flow? We record the unitary sodium current in cell-attached configuration as before and voltage clamp mode. Here we hold the membrane potential at minus 80 millivolt and we apply a depolarizing step to minus 70 millivolt. The current trace here shows that there is no current, the channel does not open. Now, if we apply a step to minus 50 millivolts, we see a large inward current. And then to minus 20, we'll see also an inward current, but smaller, and smaller at 0 millivolt, and even smaller at plus 20 millivolt. What is an inward current? I remind you that it's the inward movement of positive charges. So here, the sodium enters the neuron. Then, at plus 50 millivolts, there is no current, and at plus 60, the current is now outward, which means that the sodium ions exit the neuron. Why? When the potential is below plus 50 millivolts, the driving force is inward. And then it reverses because the equilibrium potential for sodium ions, as we have seen, is in between these two values, and it reverses and it goes in the other direction. This is only, it never happens in real life. In real life, the potential never goes up to above plus 20 millivolt. Let's build the IV curve. The IV curve, here on the right, we plot the unitary sodium current versus membrane potential at the test value, which are the values here, minus 70, 50, 20, 0, plus 20, plus 50, plus 60. How do we do that? For example, here we have this current, which is about minus 2 picoamp for minus 50 millivolts. So here, minus 2 picoamps, so the point is here. This one is around minus 1.5 picoamps, and the scale is here. And at minus 20 here. it's approximative, of 0, we can say 1, 0 here, and plus 20.5, 50, 0, and plus 60.025, something like that. So now if we trace the curve, it's a straight line. It means that the current varies linearly with the potential of the membrane in a linear fashion. If we want to write this equation with the Ohm's law, you remember from chapter 1 that unitary sodium current equals gamma, the conductance of the sodium channel, multiplied by the driving force across the membrane. This is due to the fact that the driving force is very large because the membrane potential minus 50 millivolt is far from the reversal potential of the sodium current, which is plus 50. And as we move towards the reversal potential, of course, the current is smaller because here the driving force decreases. Gamma here is the slope of this straight line, because you see here it's the form is y equals ax. A is the slope.